Right now, at this very moment, 17 comets are converging on the inner solar system. Their arrival isn't random. They're clustering around the passage of 3I Atlas, an interstellar visitor carrying chemistry that shouldn't exist in our cosmic neighborhood. As this alien object approaches the sun, the comets pulse inward like blood through cosmic arteries. When Atlas departs, they scatter again, drifting back into the dark. The solar system appears to breathe. This isn't ancient mythology or internet conspiracy. It's a pattern discovered in orbital simulations by astronomers in 2025, documented across multiple independent observations. 17 distinct objects, each following its own trajectory, yet somehow synchronized with the arrival of something from beyond our stellar borders. The timing is statistically improbable, the mechanism is unexplained, and the implications fork in directions that challenge everything we understand about how isolated bodies move through space. Tonight, we're going to investigate this unfolding anomaly with the full weight of scientific rigor and philosophical curiosity. We'll examine the hard data spectroscopy from the James Webb Space Telescope, revealing alien chemistry astrometry from survey telescopes tracking precise positions, chemical analysis that tells us where Atlas was born and what secrets it carries. We'll explore natural explanations, Oort cloud waves rippling through our icy reservoirs, debris streams from shattered parent bodies, gravitational perturbations from unseen masses lurking in the dark. We'll venture into stranger territory, dark matter interactions that leave no trace except motion artificial origins that would rewrite our understanding of intelligence in the cosmos, the possibility that we're witnessing something that doesn't fit our current models and demands we expand them. But we'll also turn the lens inward, examining whether this pulse exists in the cosmos or in the instruments and minds observing it. Because sometimes the most profound mysteries aren't written in the stars. They're written in the gap between observation and understanding, in the space where consciousness meets the universe and tries to make sense of what it sees. The stakes are higher than you might think. If Atlas is influencing these comets through some unknown mechanism, we're looking at new physics, a force or interaction we haven't cataloged, operating at scales we haven't explored. If it's coincidence amplified by how we observe, we're learning about the limits of human perception, about how easily we find patterns and randomness, about the cognitive biases that shape scientific discovery itself. And if there's even the slightest chance that Atlas represents something more than a natural comet, we're confronting questions about our place in a universe we've barely begun to explore. Questions about whether we're alone or part of a larger cosmic conversation we're only now learning to hear. Stay with me. This journey goes deep, and the deeper we go, the stranger it becomes. Picture yourself hovering above the solar system, looking down on the ecliptic plane like a cosmic cartographer mapping the architecture of our stellar neighborhood. The familiar dance unfolds below Jupiter's massive orbit, sweeping through space like a gravitational giant, Saturn's graceful arc. Decorated with its impossible rings, Earth's blue circuit around the sun, that tiny, precious orbit where everything we've ever known has happened. Predictable. Clockwork, the kind of motion that inspired Newton to write his laws and convinced humanity that the universe operates according to mathematical principles we could understand. But then you notice something else. Small dots, 17 of them, all drifting inward simultaneously. They're comets, icy remnants from the solar system's violent birth 4.5 billion years ago, normally scattered across vast distances and arriving at the inner system in ones and twos over months or years. Their appearances as irregular as rain, showers their timing determined by perturbations so ancient we can only guess at the causes. Not this time. These 17 are clustering their perihelion dates, their closest approaches to the sun, the moments when they blaze brightest and then begin their long retreat, bunched into a narrow window, spanning late 2025 into early 2026. It's like watching a school of fish sense a predator converging in response to something you can't see, moving with coordination that suggests communication or shared awareness. Even though we know fish don't plan, don't coordinate consciously, but respond to signals in ways that create the appearance of intelligence from simple rules. And there's the strangest detail, the observation that transforms this from unusual to deeply unsettling. As an object labeled 3I Atlas crosses into the inner solar system, these comets seem to move, with it pulsing toward the sun as Atlas makes its inbound journey. Then, as Atlas begins its exit in mid-2026, curving around the sun and heading back toward interstellar space, the comets scatter again, drifting back outward, like the whole system just exhaled after holding its breath. This pattern was first noticed by a user named Dobsonian Power, an amateur astronomer who spends nights watching orbital simulations, the way some people watch television, tracking the motions of bodies across centuries compressed into minutes. They posted visualizations to social media showing exactly this phenomenon, 17 dots converging as one distinctive dot moved through their midst, then dispersing in its wake. The visualization spread rapidly through astronomy communities, sparking immediate debate. Other observers validated what Dobsonian Power was seeing. Stefan Burns, posting as Astroburns online, confirmed it independently. Using different simulation software, the comets cluster while Atlas is inbound, then separate after it passes. Different tools, different datasets, same eerie result. This wasn't a single person seeing patterns in noise suffering from pareidolia or confirmation bias. Multiple sets of eyes, multiple simulations, multiple methods, all showing the same unsettling result. That's when professional astronomers started paying attention, when what began as internet curiosity became a phenomenon worth investigating with the full apparatus of modern science. So we're forced to ask uncomfortable questions, questions that challenge our assumptions about how the solar system works. Is this coincidence a statistical fluctuation where unrelated objects happen to arrive during the same window, the cosmic equivalent of 5 people reaching for the same door handle at the same moment? Is it a quirk of visualization, some artifact of how we project 3-dimensional orbits onto 2-dimensional screens, compressing time and flattening space in ways that create illusions of coordination where none exists? Or is something genuinely anomalous happening? Could Atlas be influencing these comets, somehow exerting gravitational or electromagnetic effects we don't understand, operating through mechanisms that don't appear in our textbooks? Are we witnessing a larger interstellar structure, a debris stream or gravitational wave washing through our system, of which Atlas is merely the most visible member, while the 17 comets are smaller fragments traveling in its wake? Or, and this is where conventional science starts to fray at the edges, where careers and reputations are put at risk, could this represent something designed, coordinated evidence of intelligence operating at scales we've never contemplated, using methods we can't yet imagine? The phenomenon sits at that uncomfortable threshold where natural explanation seems insufficient but extraordinary claims lack definitive proof. It's too organized to dismiss as pure randomness, as simple statistical noise that will disappear when we collect more data. Yet it's not extreme enough to demand revolutionary physics, not so far outside the bounds of known behavior that we must immediately conclude something unprecedented is happening. What makes this more than idle speculation is that we can test it. We have tools: spectroscopy to analyze chemistry and determine composition, astrometry to measure precise positions and track deviations from predicted paths, statistical methods to distinguish signal from noise and calculate probability simulations to explore what natural processes might create this pattern and what signatures they would leave. Over the next 2 hours, we're going to deploy all of them. We'll examine every hypothesis from mundane to exotic, from the most conservative explanations that preserve everything we know to the wildest speculations that would force us to reconsider fundamental assumptions. We'll look at Oort cloud dynamics, at how ancient stellar passages millions of years ago could send waves of comets inward that are only now reaching completion. We'll investigate whether dark matter concentrations or rogue planets might funnel objects toward us through gravitational corridors we haven't mapped. We'll even explore whether Atlas itself might be something other than a simple comet, whether its passage could represent first contact in a form we're not equipped to recognize, whether the universe might be stranger and more populated than our current models suggest. And crucially, we'll examine whether the pattern exists at all outside our instruments and interpretations, or whether we're the architects of our own mystery projecting order onto chaos, because that's what consciousness does. That's how brains work, by finding patterns, even when those patterns are phantoms created by the intersection of limited data and unlimited imagination. By journey's end, you'll have every piece of the puzzle: the data, the speculation, the physics, the psychology, and then you'll decide for yourself what's happening at the edge of our solar system, what this means for our understanding of cosmic mechanics, what it says about us that we care so deeply about this question, what we're really seeking when we investigate phenomena that hover at the boundary between the explicable and the mysterious. Because the universe doesn't hand us answers. It hands us clues, fragments, suggestions, and it's up to us to assemble them into understanding, or to recognize when understanding remains just beyond our reach. When humility demands we admit we don't yet know enough to choose between competing explanations, when the most honest response to mystery is wonder rather than premature conclusion. Let's reframe what we're observing through metaphor, through comparison to systems we understand more intimately. Instead of thinking about 17 individual comets and one interstellar visitor as separate actors on a cosmic stage, imagine the solar system itself as a living organism. Not alive in the biological sense. Obviously, there's no metabolism, no reproduction, no evolution through natural selection, but possessing something like rhythm, like breath, like the pulsing patterns we associate with life, even when we know the underlying mechanisms are purely physical. Systems breathe. This is a profound truth that cuts across scales and domains. Ecosystems experience seasonal cycles, periods of abundance and scarcity, growth and dormancy, the annual rhythm that shapes everything from when birds migrate to when plants flower. Weather systems pulse with high and low pressure zones, air masses expanding and contracting, creating the winds that drive ocean currents and determine whether rain falls or drought persists. Even galaxies breathe in a sense, their spiral arms compressing and releasing gas clouds in waves that trigger bursts of star formation, creating generations of stars separated by tens of millions of years. Could the solar system have a similar rhythm? A pulse in the flux of comets, a breathing pattern where more objects fall inward, during certain epochs, then fewer during others. The system inhaling debris from its periphery and exhaling it toward the sun and cycles we're only beginning to recognize. If so, what drives it? In terrestrial systems, breath is driven by pressure, differentials by temperature gradients, by the physics of gases expanding when heated and contracting when cooled. In the solar system, the analog would be gravitational perturbations, forces that periodically disturb the Oort cloud, sending cascades of comets inward like autumn leaves shaken from a tree by gusts of wind. We know such perturbations occur regularly. The Sun orbits the galactic center at approximately 220 kilometers per second, completing one circuit every 225 million years, a period sometimes called a galactic year or cosmic year. But this orbit isn't a smooth circle. The Sun moves up and down through the galactic disk every 30 million years or so, oscillating like a child on a swing. When it crosses the denser midplane gravitational interactions with giant molecular clouds, massive concentrations of gas and dust that can contain hundreds of thousands of solar masses could shake the Oort cloud like a tree in a storm, liberating comets that then take thousands or millions of years to fall inward toward the sun. Passing stars deliver similar kicks. The sun isn't isolated in space. It moves through a neighborhood populated by other stars most too distant to affect us significantly, but occasionally one passes close enough to matter. About once every million years, a star passes within a light year or so of the sun, close enough that its gravity reaches out across interstellar distances and perturbs the outer Oort cloud. The effects propagate inward over millennia, waves of gravitational disturbance rippling through the cloud like vibrations through water, eventually producing an uptick in long-period comet arrivals that can last for tens of thousands of years. Could we be seeing such a wave now? Could the 17 comets represent the crest of a perturbation that originated thousands of years ago, when some nameless star, perhaps one we've cataloged and identified, perhaps one that passed before we had instruments to notice, passed through the sun's neighborhood and sent ripples cascading through our icy reservoirs? The timing would have to be extraordinarily precise for this explanation to account for the apparent synchrony with Atlas. The wave would need to crest exactly now in 2025 when Atlas also happens to be passing through. That's a coincidence, but coincidences aren't impossible. In a universe vast enough and old enough, operating over timescales measured in billions of years, and distances measured in billions of light years, unlikely alignments become inevitable. Given enough time, every possible configuration of objects and events will eventually occur. The question is whether we're witnessing such a rare alignment or whether there's a causal connection we haven't identified. There's another metaphor worth exploring: resonance. Musical instruments resonate when sound waves match their natural frequencies, the specific vibrations at which the instrument naturally wants to oscillate. Bridges can resonate dangerously if soldiers march across them in step, their synchronized footfalls, driving oscillations that build until the structure fails. Could there be something resonant happening here, where Atlas's passage coincides with a natural periodicity in comet arrivals, and the two phenomena amplify each other in our observations, if not in physical reality? This isn't suggesting mystical connections or quantum entanglement across astronomical distances. It's acknowledging that complex systems can exhibit synchrony without direct causal links through a process called phase locking or entrainment. Cicadas emerge in massive swarms every 17 years, not because they're coordinating with each other in real time through signals or communication, but because they're all following the same internal clock set generations ago by evolutionary pressures that favored synchronized emergence. The synchrony is real. Predators get overwhelmed by sheer numbers, ensuring enough cicadas survive to reproduce. But it's indirect, mediated by shared programming, rather than direct interaction. If the solar system has periodicities, cycles in comet flux driven by orbital resonances with Jupiter and Saturn galactic tides from the Milky Way's structure, historical perturbations whose effects are still propagating inward, then what we're calling a pulse might simply be the intersection of multiple cycles a moment, where several independent rhythms happen to align like instruments in an orchestra, briefly playing the same note before diverging again. Testing this requires looking backward and forward in time. If the breathing is periodic, it should appear in historical records. Ancient astronomers documented bright comets going back millennia. Babylonians, Chinese, Arabs, Europeans all kept detailed observations of celestial phenomena, considering them important enough to preserve across generations. Medieval and Renaissance astronomers maintained meticulous records, tracking comets' paths across the sky and attempting to calculate their orbits with limited mathematical tools. Modern surveys have cataloged comets systematically for over a century, creating databases we can analyze statistically. If we plot those observations across time, looking for patterns in discovery rates and perihelion dates, do we see cycles? Bursts separated by regular intervals that would indicate periodic forcing? Or is comet arrival essentially random, following what statisticians call a Poisson process, where clustering occasionally happens by chance, but without underlying periodicity? Preliminary analysis suggests randomness with a hint of structure like static with occasional moments of clarity that might be signals or might be random fluctuations amplified by our attention. There are eras with more comets. The late 1990s saw numerous bright comets, including Hale-Bopp and Hyakutake, and eras with fewer, but no clear periodicity jumps out of the data screaming for attention. That doesn't rule out cycles. It means if they exist, they're subtle, perhaps masked by observational biases where improvements in telescope technology increased discovery rates over time, or incomplete historical records, where faint comets went unnoticed by ancient observers. The breathing metaphor also captures something psychological, something about how we relate to the phenomenon. When you watch simulations of the comet pulse, there's an almost biological quality to the motion that triggers deep pattern recognition in the human brain. Objects converge, then diverge. The system expands, contracts, expands again. It feels alive, purposeful, as if the solar system itself is a conscious entity responding to stimuli, sensing Atlas's presence and reacting in ways that suggest awareness, even though we know intellectually that rocks and ice don't think, don't feel, don't possess agency in any meaningful sense. This feeling is illusion anthropomorphism projected onto physics, the tendency to see intention where there's only causation. But it's a powerful illusion, one that's shaped human interpretation of celestial events for millennia. Ancient cultures saw divine breath in atmospheric phenomena, gods inhaling and exhaling to create wind and weather, cosmic beings whose moods determined whether crops flourished or failed. We've replaced gods with gravity breath with orbital mechanics, divine intention with physical law. But the metaphor persists because it captures something true about how complex systems behave, about the patterns that emerge from simple rules operating over long timescales. Complex gravitational systems do pulse in ways that can appear lifelike. Planetary orbits precess slowly over thousands of years, their orientations rotating like spinning tops. Moons migrate inward or outward as tidal interactions transfer angular momentum. Rings form around giant planets, organize into gaps and resonances, and eventually dissolve into spirals. These aren't random motions. They're dynamic equilibria systems, finding and maintaining patterns through the interaction of multiple forces over vast timescales, creating order from chaos through processes we can model mathematically, but that often surprise us in their complexity and beauty. The comet pulse, if it's real and physical rather than artifactual, would be one such pattern, a momentary configuration where initial conditions established billions of years ago and subsequent perturbations accumulated over millennia conspired to produce synchrony visible to observers in the early 21st century. It would teach us about the memory of the solar system, how events from the distant past echo forward through time, shaping what we observe today in ways we can only reconstruct through careful modeling and inference. And if it's not physical, if it's primarily observational or psychological, it teaches us something equally valuable: how easily we find rhythm in randomness, how naturally we impose breath on systems that don't breathe, how consciousness creates meaning by detecting patterns, whether those patterns reflect underlying order or emerge from the act of looking itself. Either way, the metaphor serves us. It gives us a framework for thinking about the phenomenon, a way to organize observations and predictions, a language for discussing something that exists at the boundary between the mechanical and the organic, between the deterministic and the emergent. It reminds us that the solar system, while governed by deterministic laws that allow us to predict planetary positions centuries in advance, exhibits behavior complex enough to surprise us, to present patterns we didn't anticipate and struggle to explain, to remain mysterious even after billions of dollars spent on telescopes and missions and research. Now let's turn our full attention to the central player in this mystery, 3I Atlas, cataloged officially as Comet C 2025 S1. The 3I designation marks it as only the third confirmed interstellar object to visit our solar system in recorded history, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Each of these visitors has challenged our understanding in different ways, forced us to expand our conception of what exists in the galaxy and how it moves through space. But Atlas is different from its predecessors in ways that make it far more puzzling, far more resistant to easy categorization. First, the trajectory. Atlas follows a hyperbolic orbit, meaning it's gravitationally unbound to our Sun. It entered from interstellar space with enough velocity that the Sun's gravity, while bending its path significantly, couldn't capture it into an ellipse. It's making one close pass and will exit back into the cosmic void, never to return. The orbit's eccentricity exceeds 1.0, the mathematical signature of an object passing through rather than captured, a visitor rather than a resident. Based on its trajectory and velocity vectors, measured with extraordinary precision by survey telescopes, worldwide, astronomers have traced Atlas's origin vector backward through time and space. It appears to come from a direction in the constellation Ursa Major, moving relative to the local standard of rest, the average motion of stars in our solar neighborhood, in ways that confirm it originated outside our solar system. But pinpointing its exact stellar birthplace is impossible given current data. Interstellar space is vast and small. Uncertainties in velocity measurements translate to enormous uncertainties in distance and time. Atlas could have been traveling for thousands of years, millions of years, even hundreds of millions of years before encountering our Sun by chance in the vastness of the Milky Way. Its perihelion closest approach to the Sun, the moment of maximum heating and maximum danger if it were to fragment, occurred around October 30, 2025 at approximately 1.4 astronomical units from the Sun. For reference and scale, Earth orbits at exactly 1.0 astronomical units by definition. Mars at about 1.5. So Atlas passed inside Earth's orbit but well outside Mercury's, threading through the inner solar system at a distance that posed no threat to our planet but brought it close enough for detailed observations. Its nearest approach to Earth measured roughly 1.8 AU, about 270 million kilometers distant, enough that it appeared as a faint smudge even in powerful telescopes, but close enough that our best instruments could dissect its light and extract secrets from its spectrum. We were safe. But proximity isn't what makes Atlas interesting or significant. What makes Atlas extraordinary is how it behaves compared to every comet we've studied before. When NASA's Swift Observatory, a space telescope primarily designed to detect gamma-ray bursts from distant cosmic explosions, trained its instruments on Atlas in early 2025 as part of a targeted campaign to study this unusual object, it detected something that immediately raised eyebrows among planetary scientists: intense water vapor emission at 2.9 astronomical units from the Sun. Most comets don't begin significant outgassing until they're inside 2 AU, deep into the region where solar radiation is strong enough to heat their surfaces substantially and sublimate the water ice that dominates their composition. The physics is straightforward. Ice absorbs sunlight, heats up, and at a certain temperature threshold begins transforming directly from solid to gas without passing through a liquid phase sublimation, the same process that makes dry ice produce those dramatic fog effects. But Atlas was hemorrhaging water while still relatively distant, its coma already expanding and bright, while solar radiation at that distance should barely have warmed its surface, like an engine firing at full throttle before it should. According to every model of comet behavior we've developed over decades of observation and theory, this suggests one of several possibilities, each interesting in its own way. Atlas might be compositionally unusual, rich in supervolatile ices like carbon monoxide or methane that sublimate at much lower temperatures than water. Carbon monoxide ice transforms to gas at around 200 degrees Celsius, cold enough that it could start outgassing while Atlas was still beyond Mars's orbit. If Atlas formed in an environment particularly rich in these supervolatiles, perhaps in the outer regions of its parent protoplanetary disk, where temperatures were coldest, it could activate early as these compounds escape, dragging water and other materials along in their outflow. Alternatively, Atlas might have internal heat sources that don't depend on solar radiation. Radioactive decay from formation isotopes like aluminum-26 or potassium-40 that release heat as they decay could warm the interior, or residual warmth from its formation or some later impact event might never have fully dissipated during its journey through interstellar space, which, despite being called cold, isn't actually at absolute zero and provides enough thermal isolation that a small object cooling purely through radiation could retain heat for millions of years. Or its structure might be such that heat penetrates deeper than typical comets, perhaps because it's more porous or has fewer insulating dust layers, warming subsurface ices and driving activity from within through cracks and fissures that vent gas into space like geysers on Saturn's moon Enceladus. Then came spectroscopy from the James Webb Space Telescope, humanity's most powerful infrared observatory positioned at a gravitationally stable point, 1.5 million kilometers from Earth. JWST turned its mirror 5 meters of gold-coated beryllium representing decades of engineering and billions of dollars toward this visitor from beyond, and revealed Atlas's chemical fingerprint in exquisite detail. The results were startling enough to prompt immediate follow-up observations and heated discussion in planetary science communities. A coma dominated by carbon dioxide with a carbon dioxide to water ratio of approximately 8:1. To understand why this matters, why astronomers immediately recognize this as highly unusual, consider that solar system comets objects formed in our own protoplanetary disk from the same material that made our planets typically show ratios much closer to 1:1 or even water dominant. Water ice is abundant in protoplanetary disks because oxygen is the third most common element in the universe after hydrogen and helium, and it readily bonds with hydrogen to form water. Carbon dioxide is present, but usually secondary, a minor component rather than the dominant volatile. Atlas flips this script entirely. Its chemistry suggests formation in an environment radically different from the one that produced our local comets, perhaps around a star with different metallicity, meaning different abundances of elements heavier than helium, or in a disk with higher carbon-to-oxygen ratios where carbon locked up oxygen before water could form efficiently, or in regions where radiation fields from the parent star or nearby massive stars preferentially destroyed water molecules through photodissociation while preserving carbon dioxide. JWST's spectroscopy also detected carbon monoxide, carbonyl sulfide, and traces of other organics, including complex hydrocarbons, that suggested photochemical processing by ultraviolet light. The spectral signature doesn't match any family of solar system comets we've studied. It's alien chemistry in the most literal sense, chemical composition, that reflects formation conditions elsewhere in the galaxy. Conditions we can only infer and model, but never directly sample unless we somehow send a probe to Atlas's origin system, wherever that might be. Polarimetry added yet another layer of strangeness, another indication that Atlas doesn't fit comfortably into our existing categories. The first, polarimetric observations conducted by ground-based telescopes, using sophisticated instruments that measure how light's electrical and magnetic field orientations change. After scattering off dust, particles revealed a deep negative polarization branch reaching 2.7% at a phase angle of about 7 degrees with an inversion angle around 17 degrees, where polarization shifts from negative to positive. These parameters might sound technical and obscure, but they're actually telling us something fundamental about Atlas's dust. Polarization describes how light scatters off particles, and the details depend critically on grain size, shape composition, and internal structure. Atlas's polarization values suggest its dust formed differently from typical comet dust, perhaps under different temperature or pressure regimes during formation, or with different mineral compositions, maybe more carbon-rich, maybe containing different silicates or metals, than the olivine and pyroxene that dominate solar system dust. It's another fingerprint pointing to exotic origins, another piece of evidence that Atlas carries material processed under conditions unlike anything in our local environment. Then there's the controversial observation from Avi Loeb, the Harvard astrophysicist, who has become something of a polarizing figure in astronomy through his willingness to propose extraordinary hypotheses about interstellar objects. Loeb suggested, based on preliminary photometry and timing of Atlas's activity, that it might be emitting its own light, not just reflecting sunlight like normal comets, but glowing from some internal process, producing luminosity that adds to reflected sunlight and would explain some anomalies in its brightness curve. This claim remains unverified by independent teams and is contentious within the astronomical community. Self-luminosity in a comet at levels detectable from Earth would require a significant energy source, concentrated radioactive decay far beyond normal levels, vigorous chemical reactions releasing light as well as heat, or something more exotic that doesn't fit conventional comet models. Natural comets don't glow on their own in ways we can detect from Earth. They shine by reflecting sunlight and fluorescing, as solar ultraviolet excites molecules in their comas, causing them to emit light at specific wavelengths. If Atlas truly generates its own light, it would be unprecedented in the study of cometary science. Loeb's speculation should be taken with substantial caution. He has a history of proposing extraordinary interpretations that often exceed what the data rigorously supports. His claim that Oumuamua might be an alien light sail generated significant media attention, but little support among experts who felt natural explanations, while incomplete, were more parsimonious than invoking alien technology. With Atlas, he's treading similar ground-pushing boundaries in ways that make many scientists uncomfortable. But the claim is testable through careful observational campaigns. Careful photometry, comparing Atlas's brightness to detailed models of pure reflected sunlight plus fluorescence from known molecular species, could reveal any excess, any contribution from internal emission. Monitoring brightness as a function of distance from the sun could distinguish between emission powered by sunlight, which should follow predictable patterns, and emission from internal sources which might show different behavior. So far, no independent confirmation has emerged from teams with no investment in the extraordinary hypothesis. Most astronomers attribute Atlas's brightness to reflected sunlight and standard fluorescence from sublimating gases, conventional cometary processes operating perhaps more vigorously than average, but not fundamentally different in kind. But the question lingers unresolved in the scientific literature, a loose thread that some find intriguing and others consider a distraction from more productive research. All these peculiarities, early outgassing, extreme carbon dioxide dominance, unusual dust properties, possible luminosity anomalies, matter because they constrain Atlas's origin story. Each observation is a clue about where and how this object formed, what stellar environment shaped its composition, what processes operated in its birth system. If its chemistry is carbon-rich, it formed in a carbon-rich environment where conditions differed from our own protoplanetary disk. If its dust structure is unusual, it experienced different formation physics, perhaps different temperatures or pressures, or radiation exposure during the era when solid grains were condensing from gas. If it outgasses early, it's either more volatile than typical comets, meaning it contains more supervolatile ices, or it's internally heated by processes we need to identify and explain. Each clue narrows the possibilities, helping us reconstruct the stellar nursery where Atlas was born billions of years ago. Was it a red dwarf system where protoplanetary disks are colder and carbon dioxide ice more stable than water ice? Was it a binary system where gravitational interactions between two stars shaped disk chemistry in complex ways? Was it a system with massive planets that migrated early during formation, disrupting the disk and ejecting planetesimals like Atlas into interstellar space before they could accrete into planets? We'll explore these questions more deeply later in this investigation. For now, hold on to this central fact. Atlas is chemically and physically distinct from our comets, a genuine interstellar messenger carrying information about environments we've never directly sampled, conditions that existed around another star in another part of the galaxy, perhaps billions of years ago. And this messenger arrived just as 17 other comets converged on the inner solar system in what appears to be an unusual concentration. Coincidence? Let's explore systematically whether it could be something more, whether connections might exist that we haven't recognized, whether Atlas's passage truly is isolated or part of a larger pattern we're only beginning to perceive. Understanding hyperbolic orbits isn't just technical detail, it's crucial to grasping why Atlas is so profoundly significant, why its presence in our solar system tells us something about the architecture of the galaxy itself. In celestial mechanics, orbits are classified by a parameter called eccentricity, represented by the letter E. This single number describes the shape of an orbit completely in terms of how elongated it is. An eccentricity of Zercho means a perfect circle like drawing with a compass. Values between 0 and 1 describe ellipses, closed repeating orbits, like those followed by planets, and most comets stretched ovals that loop endlessly around the Sun. Earth's orbit has eccentricity, 0.017, nearly circular. Halley's comet has eccentricity 0.967, a highly elongated ellipse that takes it from inside Earth's orbit out beyond Neptune.
An eccentricity of exactly 1 describes a parabola, the mathematical boundary between bound and unbound trajectories, an open curve that comes from infinity curves around the Sun and heads back to infinity, but only just barely with zero velocity at infinite distance. Objects on parabolic orbits are balanced exactly on the knife edge between capture and escape. Anything above 1 is hyperbolic. These are open curves with excess velocity trajectories that come from infinity, with some speed swing past the gravitating body once, and return to infinity with speed still remaining. They're escape trajectories, paths that cross through a gravitational field but are never captured by its visitors, that pass through once and never return. Atlas has an eccentricity greater than 1.0, confirming beyond any doubt that it's on a hyperbolic trajectory.
The Sun's gravity bent its path significantly. It came in from one direction and departed in another, its trajectory curved by the Sun's gravitational well. But that bending wasn't enough to capture it. Atlas entered with enough velocity to escape, and escape it will eventually fading from even our most powerful telescopes as it heads back into the darkness between stars, carrying with it whatever information it gathered during its brief passage through our neighborhood. But here's the profound question, the one that makes interstellar objects so fascinating to astronomers and astrobiologists. Where did that velocity come from? How did Atlas acquire the speed necessary to escape its birth system and wander between stars? Objects don't naturally achieve escape velocity without a substantial push. In our solar system, if you want to send a spacecraft to another star missions like Voyager or New Horizons, you need massive rockets generating enormous thrust and carefully planned gravitational assists from multiple planets to reach the necessary 16-17 kilometers per second relative to the Sun required to escape. It takes decades of planning, billions of dollars, and sophisticated navigation through gravitational corridors to accomplish what Atlas somehow achieved naturally. Nature has to accomplish the same feat through gravitational interactions, close encounters with planets or stars that fling objects outward at high speed through a process called gravitational scattering. Current models of planetary formation suggest this happens regularly during the chaotic era when young stellar systems are settling. Giant planets migrate inward or outward through interactions with the protoplanetary disk, gravitationally scattering smaller bodies. Planetesimals, comets, asteroids in all directions. Some of these objects crash into planets or fall into the star. Some settle into stable orbits, becoming the asteroid belt or Kuiper belt populations we observe today. And some, perhaps 1 in a million, perhaps 1 in 10 million, get ejected entirely, flung into interstellar space at speeds sufficient to cross the vast distances between stars. These ejected objects become interstellar nomads, wandering through the galaxy for millions or billions of years until chance, pure random probability in three-dimensional space, brings them near another star. Atlas is such a nomad, a fragment from some other planetary system ejected long ago, perhaps during formation, or perhaps later, through some catastrophic event like planet-planet scattering or a close encounter with a passing star that destabilized orbits throughout that distant system. Its velocity and trajectory suggest it wasn't ejected recently in cosmic terms, but has been traveling for a long time, possibly even predating our own solar system's formation 4.6 billion years ago. Stars form, age, and sometimes die on timescales relevant to Atlas's journey. The star around which Atlas formed might still exist, might have evolved into a red giant or exploded as a supernova, or might be a white dwarf slowly cooling toward eventual darkness over trillions of years. Tracing its origin requires working backward from its current trajectory, calculating where it came from by reversing its motion and accounting for gravitational perturbations from every massive object it might have encountered. You take Atlas's position and velocity measured with GPS-level precision from multiple observations, reverse them mathematically, and integrate backward through time. But this reconstruction becomes increasingly uncertain the farther back you go, because interstellar space isn't actually empty. There are gravitational perturbations from nearby stars, whose positions and masses we know imperfectly, subtle effects from galactic rotation and the Milky Way's gravitational potential, even potential interactions with dark matter concentrations if such structures exist at the predicted scales. These uncertainties accumulate exponentially, making precise origin determination impossible beyond a certain point. It's like trying to trace a raindrop's path by watching where it hits the ground. You can estimate which cloud it came from, but pinpointing which exact water vapor molecule in which exact part of the cloud is impossible, because chaos amplifies small uncertainties into large ones. The best we can say based on current trajectory reconstructions is that Atlas came from a direction roughly toward the constellation Ursa Major, covering a distance measured in parsecs, tens to hundreds of light years. Whether it originated in a specific star system we can name in our catalogs, perhaps a young star with known exoplanets, perhaps an older system we've never examined in detail, or from a region of the galaxy we've never surveyed, remains fundamentally unknown and perhaps unknowable unless future observations reveal some unexpected signature we can trace. This uncertainty is frustrating for scientists who crave definitive answers, but it's also liberating in a philosophical sense. It means Atlas carries information about environments we can't visit, stellar systems we might never identify, conditions that existed perhaps billions of years ago when its parent star was young and vibrant. Every measurement we make, every spectrum we record, every image we capture, every chemical abundance we determine is a precious sample of alien conditions, a postcard from elsewhere in the galaxy, a window into how planets form and evolve around stars that might be fundamentally different from our Sun. What about Atlas's speed? Its velocity relative to the Sun is consistent with objects ejected from typical stellar systems and drifting through what astronomers call the local standard of rest, the average motion of stars in our solar neighborhood, the frame of reference that accounts for how everything in this region of the galaxy moves together as we orbit the galactic center. It's not moving extraordinarily fast, which rules out some exotic scenarios like ejection from a supernova explosion, where speeds can reach thousands of kilometers per second, or close encounter with a black hole, where gravitational slingshots can accelerate objects to significant fractions of light speed. Its trajectory also shows no detectable signs of propulsion or course correction, no deviations from a purely ballistic path determined entirely by gravity and initial velocity, no thrust signatures that would appear as unexpected changes in acceleration, no non-gravitational forces beyond the subtle push from outgassing that affects all active comets. This is important because it constrains hypotheses about artificial origins that we'll explore later. If Atlas were a probe under intelligent control, we might expect trajectory adjustments, small course corrections to target specific destinations or maintain a desired path. So far, analysis by multiple independent teams has detected no such deviations within observational uncertainties. However, and this is crucial to maintain intellectual honesty, absence of detected thrust doesn't prove Atlas is natural. A sufficiently advanced technology might produce acceleration too subtle for current instruments to measure against the noise of normal cometary outgassing and gravitational perturbations, or might have completed all necessary course corrections before entering the region of space where our telescopes could observe it with sufficient precision to notice small changes. We're looking through a keyhole at a vast room. We see what's directly in front of us, but much remains hidden. The fundamental point is that hyperbolic trajectories tell us something profound about cosmic ecology. Atlas is a visitor, not a resident. It sampled our solar system briefly during a chance encounter lasting perhaps a year from first detection to final observations, and now it's leaving, carrying with it whatever observations or measurements its passage allowed. If it's natural, those observations are purely physical chemical exchanges with solar wind as charged particles from the sun interact with its coma, thermal stresses from solar heating that might fracture its surface or trigger buried volatiles, gravitational perturbations from planets that altered its velocity by tiny amounts. If it's artificial, a hypothesis will examine rigorously despite its improbability. Then we can only speculate what data it might be collecting about our planetary system, our sun's properties, perhaps even the electromagnetic signatures that would reveal a technological civilization on Earth. Now let's systematically catalog the crowd, the 17 actors in this cosmic drama who appear to move in synchrony with our interstellar visitor. Understanding their individual identities, their specific orbits, and their distinguishing characteristics is essential groundwork for determining whether any physical relationship exists between them and Atlas, or whether we're observing a statistical coincidence amplified by the way we collect and interpret data. The roster includes recently discovered comets like C2025R2, better known by its survey designation SWAN, after the Solar and Heliospheric Observatory's Solar Wind Anisotropies instrument that detected it. SOHO orbits the Sun at the L1 Lagrange point between Earth and Sun, giving it a constant, unobstructed view of the solar disk. Its SWAN instrument wasn't designed primarily for comet detection. It maps solar wind by observing Lyman alpha emission from hydrogen atoms, but comets release enormous amounts of hydrogen as water molecules break apart, creating bright spots in Swan's images. It has discovered dozens of comets this way, often finding objects that other surveys missed because they approach the sun from directions that are difficult for ground-based telescopes to observe. C 2025A6 designated Lemon after its discovery location was found by the Mount Lemmon Survey in Arizona, one of several ground-based programs systematically scanning the sky for near-Earth objects and comets that might pose impact hazards or simply add to our understanding of small body populations. Mount Lemmon operates a 1.5-meter telescope equipped with sensitive CCD cameras that can detect objects as faint as magnitude 21, far below what the human eye can see even through large telescopes. C-2025K1 comes from the Asteroid Terrestrial Impact Last Alert System, ATLAS, the survey network that shares its name with the interstellar visitor and operates multiple robotic telescopes in Hawaii, Chile, and South Africa. ATLAS scans the entire visible sky every night looking for anything that moves or changes brightness. It's found hundreds of asteroids and dozens of comets, fulfilling its primary mission of detecting potential Earth impactors while generating valuable data about small body populations throughout the solar system. There are also periodic comets in the mix, short-period objects that complete orbits in decades rather than centuries or millennia. Comets like 414P and 210P swing through the inner solar system on predictable schedules, their returns calculated years in advance with precision high enough to point telescopes at the right region of sky weeks before the comet becomes bright enough to see. Their presence during this particular window isn't anomalous on its own. These are known objects following known paths. Their arrivals during late 2025, scheduled by orbital mechanics, established perhaps millions of years ago. Long-period comets, objects with orbital periods measuring centuries, millennia, or even millions of years round out the count. These are Oort cloud visitors, making their first or perhaps second passage through the inner system since being scattered outward during the solar system's violent youth. Their orbits are shaped by perturbations so ancient we can only guess at the causes, perhaps a stellar flyby during the sun's youth when it was still part of its birth cluster, perhaps galactic tides acting over hundreds of millions of years, perhaps both factors operating in combination to send these particular objects on trajectories that happen to reach perihelion during our lifetimes. When you plot their perihelion dates, the specific moments they reach closest approach to the sun cross that critical distance where solar heating peaks and activity maximizes before the long retreat outward begins, on a timeline running from mid-2025 through early 2026, you see a pronounced clustering. Instead of arrivals spread relatively evenly across months or years, as you'd expect from a random population, there's a bunching, a concentration in time that statistics can quantify through measures like variance and clustering coefficients. This temporal concentration is the statistical anomaly driving this entire investigation, the observation that makes astronomers pause and wonder whether something unusual is occurring or whether we're witnessing normal statistical fluctuation amplified by observation methods and human attention. But here's where detection bias begins to complicate the simple narrative, where we must acknowledge that what we observe is shaped profoundly by how we observe. Many of these comets were found by surveys operating intensely during this particular period. Atlas, Pan-STARRS, Swan. These systems scan the sky with high cadence, finding objects because they're looking systematically and frequently with instruments sensitive enough to detect faint objects that would have escaped notice in earlier eras. If survey activity increased during this period, if funding was stable, allowing continuous operation, if weather conditions were favorable with clear skies,
If instruments were optimally calibrated and functioning without major technical issues, then the discovery rate would naturally rise. More observations means more detections, more pixels recorded, more opportunities for automated detection algorithms to flag candidates for human follow-up.
The question we must answer rigorously is whether we're finding more comets, because there are genuinely more comets arriving, because the underlying population rate increased, or because we're looking harder and more effectively than in previous years, because our detection capabilities improved and our survey coverage expanded. To disentangle this properly requires careful modeling of survey completeness, calculating what fraction of comets at various brightness levels, distances, and sky positions the surveys should theoretically detect, given their technical specifications, observing cadences, and weather statistics. Then compare observed discovery rates to those completeness-corrected predictions. If observed rates exceed predictions by margins that are statistically significant, say 3 or 4 standard deviations, enough that the probability of such a deviation occurring by chance is less than 1% or 0.1%, then you have evidence for a genuine surge in the underlying population. If observed rates match predictions within uncertainties, then the clustering might be purely observational, an artifact of how thoroughly we happen to survey during this particular window. Another major complication: orbital uncertainties that blur the temporal picture. For newly discovered comets, especially faint ones observed only a handful of times before they fade below detection limits, the orbital elements calculated by fitting mathematical curves to the sparse position. Data have large error bars. A comet that appears to reach perihelion on October 15th, based on preliminary orbit calculations, might actually peak anywhere from October 10 to October 20, or even more widely, depending on how many observations were possible and their quality. When uncertainties are large, apparent clustering can be partly an artifact of imprecise measurements that fail to resolve the true distribution of arrival times. High-quality astrometry, precise position measurements over weeks or months as comets move across the sky, building up dense data sets that tightly constrain their orbits, would reduce these uncertainties dramatically, sharpening our understanding of whether the temporal clustering is genuinely tight or whether it dissolves into a broader distribution when orbits are better determined. So far, most of the 17 comets lack such extensive observational coverage. They were discovered tracked through a few data points and then faded or moved to positions where follow-up became difficult. Gaps in coverage leave room for ambiguity that can't be resolved without additional observations that may no longer be possible if the comets have dimmed below detection thresholds. There's also the critical question of comet families, whether some of these objects are related through common ancestry, rather than representing independent random samples from the Oort cloud. Some comets are gravitationally related fragments of larger parent bodies that broke apart through tidal stresses, rotational breakup, or collisions, then dispersed along similar orbits like beads on a string. The Kreutz sungrazer family is the most spectacular example, comprising dozens of comets that all dive extremely close to the Sun, some passing within solar radii, all originating from a single large progenitor that fragmented centuries or millennia ago.
These comets share similar orbital elements, similar perihelion distances, similar orbital planes, similar eccentricities, because they started from a common source and haven't been perturbed enough over time to erase the family resemblance. Could some of the 17 belong to known families? If so, their simultaneous arrival might simply reflect the family's natural orbital distribution, rather than representing a new phenomenon requiring exotic explanation. Checking family affiliations requires comparing orbital elements, systematically inclination, longitude of ascending node, argument of perihelion distance itself, against catalogs of known groups that have been painstakingly assembled over decades of observation and analysis. Preliminary checks suggest most of the 17 aren't members of recognized families. They show diverse orbital parameters across all elements pointing to independent origins scattered throughout the Oort cloud rather than shared ancestry. But exhaustive family analysis accounting for all known groups and testing for potential new families hasn't been completed. Some relationships might only become clear with better orbital data or more sophisticated dynamical modeling that traces orbits backward through thousands of years to look for past close approaches that would indicate common origin. Interestingly, the diversity itself is intriguing from a scientific standpoint. If all the comets were long period with similar characteristics, you might expect some coherence in their properties. Similar semi-major axes indicating they came from similar distances in the Oort cloud. Similar aphelia showing where their orbits reach farthest from the Sun, maybe even similar inclinations if they originated from a specific sector perturbed by a specific event. But the mix we observe includes long-period comets with wildly different orbital characteristics, plus short-period comets with completely different dynamical histories. This heterogeneity makes constructing coherent origin scenarios more difficult. It's easier to explain a homogeneous group than a diverse one. It's analogous to finding a crowd of people at a train station. Are they gathering for a reason, waiting for the same train, attending the same event, following the same schedule? Or did they simply converge by chance, each following independent plans that happened to intersect at this location? And time, the uniformity or diversity of the crowd, provides clues. If everyone's dressed formally, they might be attending a wedding. If they're wearing hiking gear, maybe there's a popular trail nearby. But if clothing styles ages and behaviors are completely random, convergence is probably coincidental. The 17 comets are like that diverse crowd, hard to fit into a single narrative resistant to simple explanations that would unite them under a common cause. And that resistance might be telling us something important, that the clustering, while statistically unusual, might not have a single unifying explanation, but rather represents the chance alignment of multiple independent processes occurring simultaneously. The question then becomes, how unusual is it really? How often would we expect to see such clustering purely by chance if we observed for long enough? The answer requires Monte Carlo simulations, computational experiments where you generate thousands of synthetic comet populations with realistic parameters drawn from historical distributions. Then count how frequently those synthetic populations exhibit clustering as tight as or tighter than what we observe. If tight clustering appears, frequently, say 10% of simulations show something similar, then the observed pattern isn't particularly surprising. If clustering this tight appears rarely less than 1% of simulations, then we have a puzzle requiring explanation. Such simulations haven't been published in peer-reviewed literature yet, at least not addressing this specific clustering with the rigor necessary to draw firm conclusions. Preliminary estimates based on simpler models suggest clustering like this is rare, but not astronomically so, perhaps occurring a few times per century if you monitor continuously. That puts it in an ambiguous zone between definitely unusual and worth investigating, and so rare it demands revolutionary explanations. It's interesting without being definitive, suggestive without being conclusive. This is the honest assessment we must make at this stage. We don't have enough high-quality data yet to determine whether the clustering represents coordinated motion, chance alignment, or something intermediate.
The evidence leans toward coincidence amplified by observational effects and human pattern recognition. But we cannot rule out that something genuinely anomalous is happening at a level we haven't yet detected or understood. And so the mystery persists, suspended between the known and unknown, waiting for additional data to tip the balance one direction or another, waiting for time and observation to reveal whether this pulse is physical reality or perceptual artifact. Here's where the investigation takes a philosophical turn, where we must confront how observation shapes reality in ways both subtle and profound. The comet pulse is most dramatically visible in certain types of visualizations, specifically simulations that display the solar system from above the ecliptic plane, with time compressed so years pass in seconds and orbits projected onto a flat surface like maps, projecting the three-dimensional Earth onto two-dimensional paper. These visualizations are extraordinarily powerful tools for understanding orbital mechanics, for grasping patterns that unfold over timescales too long for direct human observation. They let us see the solar system's choreography, the elegant dance of planets and smaller bodies moving according to Newton's laws and Einstein's refinements. They compress decades into minutes, making the imperceptible perceptible, revealing structure hidden in the raw data of positions and times. But they're also distorting mirrors, introducing artifacts that can mislead even careful observers who understand orbital mechanics intimately. The distortions aren't errors or mistakes, they're necessary consequences of translating high-dimensional reality into formats human brains can process. But they shape perception in ways we must account for when interpreting what we see. The most significant distortion is dimensional compression, the flattening of three-dimensional space into two-dimensional representations. Orbits exist in three-dimensional space, following curves through volume. But screens and paper are two-dimensional surfaces. To display orbit simulations must project them onto a plane, usually the ecliptic. The flat disk, where Earth and most planets orbit the natural reference plane for describing solar system motion. Planets respect the ecliptic reasonably well because they formed from a protoplanetary disk that was thin and flat, with most material concentrated in a plane. Their orbits deviate slightly. Venus tilted by 3 degrees, Mars by 2, Jupiter by 1. But these inclinations are small enough that planetary motion appears nearly coplanar when viewed from far away. Comets, however, don't respect the ecliptic at all. They arrive at steep angles, diving down from above or below their orbital planes, tilted wildly relative to the planetary disk. Some approach perpendicular to the ecliptic, coming straight down from galactic north or up from galactic south. Others arrive at intermediate angles, cutting through the planetary plane like cars entering a traffic circle from different directions. When you project these inclined orbits onto the flat ecliptic plane, geometric effects create illusions. Paths that are actually separated by millions of kilometers in three-dimensional space can appear to intersect or run parallel in the two-dimensional projection. Objects at very different distances can appear close together. The third dimension collapses, and with it collapses accurate representation of spatial relationships. It's analogous to looking at a globe from directly above the North Pole. Lines of longitude converge at the pole on this view, appearing to intersect at a single point. But those same lines are actually parallel at the equator, separated by thousands of kilometers. The convergence is an artifact of perspective, of flattening three-dimensional geometry onto two-dimensional perception. The same principle operates with comet orbits. Convergence in projection doesn't equal convergence in reality. Objects that appear to cluster tightly when viewed from above might be scattered across vast volumes when seen from other angles. Temporal compression adds another layer of potential distortion. Real orbital motion is slow on human timescales. Comets take months to move from the outer solar system to perihelion years to complete full orbits. But simulations speed this up dramatically, making years pass in seconds, compressing time by factors of millions or billions. Motion that's gradual becomes rapid, and subtle differences in timing get compressed into what looks like perfect simultaneity. Imagine filming cars entering a shopping mall parking lot over the course of an entire day, then playing the footage back at 10,000 times normal speed. Cars that arrived hours apart would seem to arrive together, flowing into parking spaces in what appears to be a coordinated stream. The simultaneity is an artifact of temporal compression, not evidence of coordination among drivers. Comet simulations do exactly this. They compress months or years of motion into visual timescales we can comprehend, and in doing so they create apparent synchrony that might not reflect the true temporal distribution of arrivals. To test whether the pulse is real, spatial-temporal coordination or artifactual, you must examine the data from multiple perspectives, systematically varying the parameters that shape visualization. Rotate the viewing angle, look at the solar system edge-on instead of from above or from arbitrary oblique angles that don't privilege any particular plane. Change the time compression, slow it down to show real-time motion over hours. Or days, speed it up even more, to show centuries in seconds, or examine static snapshots at specific moments rather than continuous animation. Use different projection methods, orthographic, which preserves angles, perspective, which mimics human vision, stereographic, which preserves circles, each emphasizing different geometric properties. When researchers performed these systematic variations, testing whether the pulse persisted across different viewing conditions, something interesting emerged. The pulse weakened. From certain viewing angles, the clustering was less pronounced, appearing more like random scatter than organized convergence. With different time compression rates, the synchrony seemed less impressive, more like normal variation in arrival times. With edge-on views that emphasize the three-dimensional structure, the tight grouping and the flat projection dissolved into a more diffuse distribution spread across the vertical dimension that the flat view had hidden. The phenomenon didn't disappear entirely when visualizations changed. There's still temporal clustering in perihelion dates that exists independent of how you choose to visualize it, but it became less dramatic, less compelling, less obviously demanding explanation. This suggests that at least some of the apparent coordination is perceptual rather than physical, shaped by the particular ways we choose to represent orbital motion in forms human cognition can grasp. This doesn't mean the pulse is entirely fake or that the investigation is worthless. It means visual impressions are unreliable guides to truth, and we need quantitative methods to separate signal from noise, to distinguish between real patterns in the data and patterns in how we display the data. Instead of relying on what simulations look like, which depends sensitively on arbitrary visualization choices, we need to analyze the actual numbers. Calculate statistical measures of clustering that are invariant to viewing angle and time compression. Compare observed distributions to random models, using rigorous hypothesis testing test whether patterns are significant relative to appropriate null hypotheses. There's also deep human perception bias that operates independent of technical visualization choices. Our brains are pattern recognition engines evolved through millions of years of natural selection to detect faces in clouds, hear words in random noise, find order in chaos. This cognitive tendency is usually adaptive. It helps us survive by identifying threats and opportunities quickly, by extracting signal from noisy sensory data, by finding causal relationships that let us predict what comes next. Spotting the tiger hidden in foliage, recognizing the telltale rustling that indicates a predator or prey, seeing patterns in weather that indicate coming storms. These abilities conferred survival advantages on our ancestors, and they're hardwired into our neural architecture. But this same tendency becomes a liability in science, where we need to distinguish real patterns from imagined ones, where statistical rigor must override intuitive pattern matching that can lead us astray. When we know there's an interstellar object in the system, when we're primed to look for unusual effects associated with this visitor from beyond, we're cognitively more likely to see patterns, even if they're not there. This is confirmation bias, the tendency to notice and remember information supporting what we already believe, while dismissing or forgetting information that contradicts it. To guard against this, scientists use techniques like blinding, where analysts don't know what they're looking for until after they've processed the data, preventing expectations from shaping results. They use control groups, comparing the phenomenon of interest to baseline conditions to see if differences are significant. They pre-register hypotheses committing to specific predictions before collecting data to prevent cherry-picking patterns that happen to appear interesting after the fact. For the comet pulse, these safeguards weren't in place initially because it wasn't a designed experiment. It was a serendipitous observation, a pattern noticed by people exploring data and simulations without specific hypotheses about what they might find. That makes assessing its reality harder because we can't rule out that observer bias played significant roles in its discovery and subsequent amplification through social media and informal scientific networks. The philosophical question underneath all this is profound and difficult. What does it mean for a pattern to be real when reality is always observed, always filtered through instruments and perception, always represented through choices about visualization and analysis? If a configuration of orbits looks synchronized from one angle but random from another, which perspective is correct? If clustering appears significant with one statistical test but not with another, which test should we trust? If human cognition naturally imposes order on randomness, how do we know when we've found genuine order versus creating it through observation? Reality in a deep sense is multi-layered and perspective-dependent. There's the physical reality of objects following trajectories determined by forces and initial conditions, the fundamental level where mathematics describes motion with precision. There's the observational reality of what our instruments can detect and measure, limited by sensitivity and viewing geometry. There's the analytical reality of what statistical methods reveal, shaped by choices about models and significance thresholds. And there's the perceptual reality of what human cognition constructs from all the above, integrating information across layers while introducing biases and distortions characteristic of how brains work. The comet pulse exists differently at each layer. Physically, 17 comets are genuinely arriving during a relatively narrow window that's not disputed. Their existence is confirmed by photographs and measurements. Observationally, surveys detected them and recorded their orbits, also not disputed. The data exists in archives. Analytically, whether their clustering is statistically significant depends on which methods you apply and how you define the boundaries of the phenomenon. Perceptually, the impression of synchrony is strong in some visualizations and weak in others, shaped by how we display the data and how our pattern recognition systems respond. Truth resides somewhere in the intersection of these layers, in the overlap region, where physical reality, observational capability, analytical rigor, and perceptual interpretation all converge. Our task is to navigate these layers, carefully acknowledging the limitations of each perspective while synthesizing them into the most accurate picture possible, resisting both the temptation to dismiss everything as artifact and the temptation to accept surface appearances without rigorous validation. This is science at its most mature and most challenging, not seeking simple yes or no answers to questions that might not have yes or no answers, but recognizing that reality is complex, multifaceted, and often resists the tidy categories we try to impose. The comet pulse is teaching us about those complexities, about how observation shapes understanding, about the gap between what is and what we perceive, about the necessity of bringing multiple perspectives and methods to bear on phenomena that exist at the boundaries of the known. Modern astronomy runs on artificial intelligence. Not the science fiction kind with consciousness and goals, but practical algorithms processing data faster and more thoroughly than humans could manage. Every night, survey telescopes generate terabytes, thousands of billions of bytes of images, millions of individual detections, thousands of potential transients requiring follow-up. Human astronomers couldn't examine even 1% of this deluge manually. They need automated systems sifting through noise, flagging interesting candidates, prioritizing which deserve precious telescope time for confirmation and detailed study. Machine learning algorithms excel at this task when properly trained. Fed databases of known objects, supernova, variable stars, asteroids, comets, they learn to recognize patterns distinctive to each class. Light curves that rise rapidly and decay slowly suggest supernova. Proper motion across multiple nights indicates asteroids. Diffuse extended appearances signal comets. When new observations arrive, algorithms classify them probabilistically, assigning confidence scores that help astronomers decide what to follow up. This technology is transformative, enabling discoveries that would otherwise remain hidden in the data flood. But it's not perfect, and its imperfections are directly relevant to whether the comet pulse is real or algorithmic artifact. Recent research from Oxford and Google Cloud demonstrated both the power and the pitfalls. They trained Gemini, a general-purpose AI model, to classify cosmic events. Performance was impressive accuracy, matching or exceeding specialized algorithms hand-tuned for specific tasks. But the real innovation was explainability. The model could articulate its reasoning in natural language. This appears to be a supernova because of the light curve shape and lack of proper motion. This appears to be a comet because of the diffuse coma and tail direction. Explainability is crucial for trust. When AI flags an object as interesting and astronomers invest observing time following it up, they need to understand why the AI made that decision. Was it based on physical characteristics that make astrophysical sense, or did the AI latch onto spurious correlations, artifacts in training data with no connection to real astronomy? When researchers examined Gemini's internal representations, they found it was sometimes keying on unexpected features, image processing artifacts, instrumental characteristics, quirks of specific telescopes, rather than purely physical properties. The model was finding patterns, yes, but not always the patterns humans intended it to find. This is algorithmic hallucination. The AI sees correlations in data that are statistically real, but physically meaningless patterns in how we collect data, rather than in the phenomena themselves. Could this affect the comet pulse? If AI systems processed survey data, grouped detections, flagged candidates for human examination, they might have introduced subtle biases, amplifying the appearance of synchrony. Perhaps comets discovered during certain observing windows got classified similarly based on instrumental signatures rather than physical properties. Perhaps the AI's grouping algorithms, designed to cluster similar objects, created apparent relationships where none exist physically. The AI didn't intend to create patterns. Algorithms have no intentions, but processing shaped what humans subsequently observed, potentially creating feedback loops where initial classifications influenced later observations, which then confirmed the initial pattern, bootstrapping a phenomenon into existence through the interaction of algorithmic bias and human attention. There's also temporal aliasing from how surveys operate. They observe certain sky regions on certain nights, determined by scheduling algorithms balancing multiple scientific priorities. Weather interrupts. Moon phase affects which fields are observable. Instrument maintenance creates gaps. If comets happen to be discovered during intensive observing periods, that could create apparent temporal clustering, reflecting the observing schedule more than physical arrival times. AI can amplify this through what computer scientists call sampling bias. If the training data overrepresents certain types of observations or certain time periods, the trained algorithm becomes better at finding similar patterns, creating self-reinforcing biases, where the AI finds what it was taught to find even when presented with different phenomena. The solution is transparency and redundancy. We need open-source algorithms where anyone can examine the code. We need multiple independent AI systems processing the same data with different architectures and training sets. If all agree on patterns, confidence increases. If patterns appear only with certain systems, they're likely artifactual. Let's approach this from pure physics and mathematics. If the comets were genuinely responding to Atlas through some physical coupling, what would we expect to see in their orbital elements? Orbital elements completely specify motion, semi-major axis orbit size, eccentricity, elongation, inclination, tilt, longitude of ascending node where the orbit crosses the ecliptic going northward, argument of perihelion. Orientation of the long axis mean anomaly position along the orbit at a reference time. These 6 numbers contain everything knowable about an orbit. If comets share common origin, fragments of a parent body or members of a debris stream, orbital elements should cluster.
Similar inclinations, similar nodes, similar arguments of perihelion. Radiant directions pointing back toward a common source region. Perturbations scatter them over time, but family resemblances persist for millions of years. Analysis of the 17 comets shows mixed results. Some similarities exist, a few have inclinations around 30–40 degrees, but scatter dominates. Nodes span the full 360-degree range. Arguments of perihelion show no preference. At first, inspection elements appear random, but uncertainties matter critically. For newly discovered faint comets, observed briefly, orbital elements have large error bars. An apparent inclination of 30 degrees might actually range from 25 to 35 degrees, depending on observation quality. When uncertainties are large, apparent scatter can hide real clustering, or apparent clustering can be random fluctuation within error bars. High-precision astrometry over extended periods would reduce uncertainties, sharpening the picture. But most comets lack such coverage, discovered, observed briefly, then fading below detection limits before comprehensive tracking was possible. Could Atlas itself gravitationally affect the comets? Simple calculation says no. Atlas is small, perhaps 5 kilometers across, based on brightness and assumed albedo. Its mass is maybe 10⁻15 kilograms. At distances of millions of kilometers separating it from other comets, gravitational force is utterly negligible, orders of magnitude, too weak to significantly perturb orbits on human timescales. If Atlas influences them, it must be through something other than gravity, electromagnetic interactions, radiation pressure, or mechanisms we haven't considered. But each alternative faces severe problems. Electromagnetic coupling requires unrealistic field strengths. Radiation pressure needs luminosity far exceeding observations. Exotic mechanisms lack both theoretical foundation and empirical evidence. The most parsimonious explanation remains. Coincidence: 17 comets arriving during a narrow window is unusual but not impossible. Statistical fluctuations occur. Given enough observations over enough time, rare configurations inevitably appear. Testing requires Monte Carlo simulations, generate thousands of synthetic comet populations with randomized arrival times drawn from historical distributions. Count how often you get clusters of 17 or more within 6-month windows. If frequently, the observed pattern isn't surprising. If rarely, we need explanation. Such rigorous simulations haven't been published yet. Preliminary estimates suggest clustering like this occurs perhaps once per century, rare enough to notice, common enough that invoking new physics seems premature. The honest assessment: insufficient data to determine whether coordination is real. Evidence leans toward coincidence amplified by observation methods, but genuine anomalies can't be ruled out. Science depends on verification. One observation isn't enough. You need independent confirmation, multiple data sources, reproducible results. Without verification, claims remain tentative possibilities rather than established facts. The comet pulse faces verification challenges on multiple fronts. First, institutional gaps. Early 2025 saw a U.S. government shutdown affecting NASA and related agencies, reducing observing time and delaying data releases.
While resolved, it created information blind spots periods when surveys operated at reduced capacity or data processing lagged significantly behind collection. Could the pulse be partly artifactual from these gaps? If observations were sparse during certain periods, then clustered when surveys resumed full operation, that could create apparent synchrony in discoveries reflecting observing cadence rather than actual arrival distribution. Second, publication bias. Positive results. Showing effects or patterns get published more readily than null results. If several teams analyzed comet data and most found nothing unusual while one found clustering, the clustering study might get shared widely, while null results remain unpublished, creating distorted impressions of evidentiary strength. Third, retroactive pattern finding. The pulse wasn't predicted in advance, it was noticed afterward. When searching for patterns after data collection, you risk finding spurious correlations that emerge from random noise simply because you're looking. Pre-registration prevents this by committing to specific hypotheses before data collection. The pulse can't be pre-registered, it's already observed. But future predictions can be providing tests of whether patterns persist. Fourth, replication. For verification, independent teams using independent data need to confirm findings, ideally using different instruments, different analysis methods, different assumptions. If all roads lead to the same conclusion, confidence increases. If the pattern appears only with certain methods or data sets, it's likely artifactual. Replication remains incomplete. Multiple observers saw patterns in simulations, which encourages. But detailed statistical analysis from independent groups hasn't been published in peer-reviewed venues. The phenomenon exists in liminal state observed, but not fully verified, interesting, but not conclusive. This is normal for early-stage discoveries. Most findings pass through this ambiguous phase where initial excitement meets methodological scrutiny. Some survive and become established facts. Others dissolve under examination, revealed as artifacts or errors. Where the comet pulse lands remains to be seen. More data arrives daily as comets approach perihelion and observing campaigns intensify. The next months are crucial for determining whether this mystery has substance or teaches us about pattern seeking in noisy data. Humans have always seen messages in the sky. Long before telescopes, ancient cultures interpreted celestial events as divine communication. Babylonian astronomers called comets hairy stars, associating them with kings' deaths or wars. Chinese catalogs spanning millennia assigned political significance to comets. Medieval Europeans saw them as harbingers of plague and famine. This wasn't irrational superstition, but attempts to find meaning in celestial events to connect heaven and earth to impose order on a seemingly capricious cosmos. Modern science replaced omens with orbital mechanics. We understand comets as natural objects, not messages, but the impulse remains. We still want the universe to speak to us. The comet pulse taps into that ancient impulse. An interstellar visitor arriving as 17 comets converge feels meaningful, like the universe trying to tell us something. Maybe we're not alone. Atlas is a probe, a messenger from another civilization, and its passage is deliberate, coordinated, designed to attract attention. Or maybe it reveals natural processes we don't understand, showing us how the cosmos organizes itself in ways transcending our models. Or maybe the hard truth, it tells us nothing. Maybe meaning is something we bring to the cosmos, not something we find there. Maybe the universe is indifferent, operating according to laws that don't care whether we understand them. Comparative mythology offers interesting parallels. Many cultures have sky herald myths, celestial visitors bringing knowledge or warning. The Hopi blue star, Kachina, appearing before times of change. Babylonian watchers observing human affairs. Vedic Vimanas carrying divine messengers. These myths aren't evidence of ancient alien contact, they're evidence of universal human psychology. We've always looked up, always wondered, always tried to connect celestial phenomena to terrestrial concerns. The comet pulse is modern continuation of that tradition. We've replaced gods with physics, omens with orbital elements, but the underlying pattern remains: observe something unusual, construct narratives to explain it. Narratives that reveal as much about us as about the phenomenon itself. In the 21st century, science documentaries serve quasi-religious functions. People don't just watch for information, they watch for meaning, connection, the emotional experience of awe. Long-form content designed for bedtime listening provides meditation, contemplation of something vast and humbling, feeling small in a good way, connected to the cosmos rather than alienated from it. Neuroscience research confirms experiencing awe produces measurable psychological benefits: reduced stress, decreased inflammation, improved mood, increased prosocial behavior. Awe is medicine for the modern mind. And for many disconnected from traditional religious practices, cosmic mysteries provide awe in accessible form. The comet pulse offers exactly this. Strange enough to provoke wonder, but grounded enough to feel real. It doesn't require faith, it requires attention, curiosity, willingness to sit with ambiguity. This is rational wonder that doesn't abandon reason but uses reason as a tool for deeper exploration. It entertains possibilities without endorsing them prematurely. Rational wonder balances two extremes. One side, rigid skepticism, dismissing anything unusual as nonsense, clinging to the known, resisting the new. This protects against error, but at the cost of discovery. Other side, uncritical belief, accepting any claim without evidence, collapsing into conspiracy thinking and pseudoscience. This feels imaginative but leads nowhere good. Rational wonder walks between these extremes, saying, "This is strange. Let's investigate rigorously. Let's test hypotheses, gather data, follow evidence wherever it leads. But let's also stay open, acknowledging the universe has surprised us before and will again." This mindset is increasingly rare and increasingly necessary. In an age of information overload, distinguishing truth from noise is harder than ever. Rational wonder is a cognitive skill worth cultivating, and cosmic mysteries provide practice. Jung proposed that we project our unconscious onto external reality, seeing in the world what we carry inside. The cosmos becomes a mirror reflecting our fears, hopes, desires back at us. When we look at the comet pulse, what are we seeing? 17 icy objects and one interstellar visitor, or 17 manifestations of our own uncertainty orbiting around a foreign element we can't quite categorize. Every comet we track is, in a sense, an emotion we've launched into orbit. Fear of catastrophe, will it hit us? Hope for revelation, will it teach us something new? Longing for connection. Are we alone, or does it represent contact? Atlas embodies ultimate otherness, not just from another part of our solar system, but from beyond it entirely. It's literally alien chemistry formed under conditions we've never sampled, carrying information about environments we may never visit. Our fascination isn't purely scientific, it's existential. Atlas represents the unknown, the frontier, the possibility that our understanding is incomplete and that completion might come from unexpected directions. The 17 comets clustering around it could represent our attempts to make sense of the unknown, to surround it with familiar categories, to domesticate it through classification. Or Jung's insight, the clustering might be us projecting coherence onto randomness, imposing pattern. Because that's what consciousness does. We can't help but organize, categorize, narrativize. It's how we function. The question isn't whether this psychological process happens, it definitely does. The question is whether it's the whole story or whether there's also physical story underneath. Science provides methods for separating these layers, testing whether patterns exist, independent of perception. But science is practiced by humans who bring psychology to the work. We're never fully objective. This doesn't invalidate science. It means science must be practiced with humility, awareness of its own limits, willingness to question not just the data, but the questions we ask of it. Let's venture into uncomfortable territory, the possibility that Atlas isn't entirely natural. This is emphatic speculation without definitive evidence, but it's worth exploring to understand why the idea is tempting and what testing would require. The alien hypothesis rests on Atlas's anomalies: early outgassing, extreme carbon dioxide ratio, possible self-emission, unusual polarimetry. None definitively prove artificiality. All can be explained by natural processes, but taken together, they create a profile that doesn't quite fit. What would Atlas being artificial mean? First, internal power source. Natural comets are powered by sunlight. If Atlas has energy reserves, nuclear chemical exotic, that could explain early outgassing and potential self-luminosity. Second structure. Artificial objects have geometric features, symmetry, straight edges, non-random configurations. Natural comets are lumpy rubble piles. High-resolution imaging could distinguish between these, but we lack images sharp enough to resolve Atlas's shape and detail. Third, trajectory adjustments, course corrections impossible for passive objects. Analysis shows no such deviations yet. Its path appears ballistic, but subtle adjustments hiding in observational noise can't be ruled out. Fourth, signals. Radio telescopes could scan Atlas for artificial emissions. So far, no SETI observations have been reported publicly. The comet clustering adds another layer. If Atlas were artificial, could it activate other comets, trigger outgassing through radiation particles or unknown mechanisms? The energy requirements seem prohibitive. To heat 17 comets at millions of kilometers distances, Atlas would need to be extraordinarily luminous, far beyond observations. History offers cautionary lessons.
The face on Mars. Tabby's star. Oumuamua all generated speculation, all turned out to have natural explanations, or remain too ambiguous to conclude anything. Loeb's claim that Oumuamua might be an alien light sail generated media attention, but little expert support who felt natural explanations were more parsimonious. With Atlas, Loeb treads similar ground-pushing boundaries in ways that make many scientists uncomfortable. His speculation about self-luminosity hasn't been independently confirmed. Most astronomers attribute Atlas's brightness to reflected sunlight and standard fluorescence. But the claim is testable. Careful photometry, comparing brightness to models, could reveal excess emission. Monitoring brightness versus distance from the sun could distinguish between solar-powered and internally powered emission. If any of the 17 comets brighten, detailed spectroscopy could test whether their chemistry matches Atlas, supporting the debris train hypothesis.
The meta point, the alien hypothesis, forces us to ask, what evidence would convince us? What would it take to conclude an object is artificial? This isn't idle. As we discover more interstellar objects, we need frameworks for assessment. Most will be natural, but probability allows that eventually one might not be. The comet pulse is practice a test case for how we think about anomalies, how we balance skepticism and openness, how we investigate claims, pushing boundaries without abandoning rigor. Here's a hypothesis grounded in mainstream physics, but still exotic. What if the comet pulse is caused by invisible mass we can't detect directly, but can infer from gravitational effects? Dark matter is the leading candidate. This mysterious substance makes up about 85% of the universe's matter, yet we've never detected a particle directly. We infer its existence from gravitational effects. Galaxies rotate too fast. Clusters bend light too much. Cosmic microwave background has fluctuations requiring more mass than we can see. Dark matter doesn't emit light, doesn't absorb light, doesn't interact electromagnetically. As far as we know, it interacts only through gravity. That makes it extraordinarily hard to detect directly. but the gravitational evidence is overwhelming. Current models suggest dark matter clumps into subhalos smaller concentrations embedded within the larger galactic halo. These range in mass from thousands to millions of solar masses, though some theories predict even smaller ones down to planetary masses. If a dark matter subhalo passed through the Oort cloud, it could gravitationally perturb comets, sending a packet inward. The subhalo itself would be invisible, leaving no electromagnetic signature, but its effects would persist in altered comet trajectories. The timing a subhalo passed through the inner Oort cloud thousands of years ago, affected comets began falling inward. Those journeys are completing now in 2025, producing the observed cluster. Atlas's arrival during the same window would be coincidence, two independent events overlapping. The hypothesis makes predictions. If a subhalo caused clustering affected comets should show coherence in orbital elements. Similar velocity vectors, radiant directions pointing back to common origin. Testing requires high-precision astrometry and careful dynamical modeling. There are alternative dark perturbers, rogue planets or brown dwarfs wandering interstellar space. These aren't dark matter. They're ordinary matter, just not bound to any star. Billions of rogues likely exist in the galaxy, ejected during formation or later through gravitational interactions. If one passed through the Oort cloud, it could scatter comets like a subhalo. But rogues emit thermal radiation, faint infrared glow from residual heat. Surveys like WISE have searched for such objects and found candidates, though none close enough or massive enough to explain the pulse. There's also Planet 9, the hypothetical super-Earth thought to orbit in the outer solar system. Its existence is inferred from unusual clustering of trans-Neptunian objects. If Planet 9 exists, it could perturb Oort cloud comets over long timescales. But its orbit is thought to be stable, producing steady perturbations rather than sudden bursts. The dark perturber hypothesis is attractive because it explains clustering without requiring Atlas to do anything, but it has weaknesses. Dark matter subhalos are hypothetical at solar system scales. Rogues are real but hard to find. Planet 9 is itself unconfirmed. We're explaining one mystery by invoking another. That's not necessarily wrong. Dark matter is real even undetected directly, but it's not satisfying. Ideally, we'd have independent evidence for the perturber before using it to explain clustering. That evidence might come. Future surveys might detect thermal emission from rogues or gravitational perturbations from subhalos. Until then, the dark perturber remains plausible enough to take seriously, but speculative enough not to embrace prematurely. Here's the wildest speculation, the edge where physics meets philosophy. What if the pattern reflects something we don't have concepts for yet? What if there are organizing principles beyond the forces we've cataloged? This isn't proposing magic or abandoning materialism. It's acknowledging our current models might be incomplete in ways we don't yet recognize. Historically, this has happened before. Before Newton, action at a distance seemed impossible. Before Maxwell, electricity and magnetism weren't unified. Before Einstein, space and time weren't woven together. Each revolution introduced concepts previous generations couldn't formulate. Could we be in similar position now, missing a framework that would make the comet pulse immediately comprehensible? One speculative direction involves information as fundamental as matter and energy woven into reality's fabric. If information organizes systems, could there be informational fields influencing how objects behave? This is highly controversial. Most physicists argue all phenomena reduce to known forces, but a minority explores whether complexity itself has organizing power we haven't formalized. Another direction is emergence, when complex systems exhibit behaviors unpredictable from components alone. Consciousness emerges from neurons' life, from chemistry, weather, from thermodynamics.
Could there be emergent gravitational effects patterns arising when many objects interact over long timescales in ways not reducing to simple pairwise forces? Three-body problems already exhibit chaos and emergent structure. Lagrange points, Trojan asteroids, orbital resonances. These aren't new forces. They're complex outcomes of gravity in multi-body systems. Maybe the Oort cloud with trillions of objects exhibits emergent dynamics we haven't mapped. Testing would require massive computational resources modeling not just 17 comets, but the full Oort cloud running simulations over millions of years to see what patterns emerge. Such work hasn't been done, partly because computational cost is enormous, partly because we lack complete data on Oort cloud structure. There's also anthropic selection. We observe what we're capable of observing, which creates apparent patterns. If our instruments and methods bias us toward detecting certain clustering types, we'll find clustering even if underlying distribution is random. The silent architect metaphor captures the sense that maybe there's order we don't recognize structure beyond current frameworks. Maybe the universe is more organized than we think, or less organized than we hope, and patterns we see are projections. Either way, speculation serves a purpose. It keeps us humble, aware that understanding is provisional, that today's impossible might be tomorrow's textbook. Quantum mechanics teaches that observation affects reality at the smallest scales. Measure a particle's position, disturb its momentum. The observer is entangled with the observed in ways challenging classical intuition. Does something analogous happen? Observing the cosmos. Not through quantum effects, those wash out at large scales, but through choices inherent in observation. Every observation involves decisions: where to point telescopes, what wavelengths to measure, how long to expose which objects to follow up. These decisions shape what we discover, creating feedback loops between observer and observed. The comet pulse might be caught in such a loop. We noticed Atlas, an unusual object. Naturally, we looked for effects anything correlated with its passage. We found clustering, or created the impression of clustering through how we searched, what we emphasized, what we studied. This isn't suggesting fraud or incompetence. It's acknowledging observation is never neutral. Questions we ask shape answers we get. There's also the problem of defining the phenomenon. What counts as the comet pulse? 17 comets, why not 16 or 18? Late 2025, why not extend to mid-2026 or go back to early 2025? The boundaries we draw are somewhat arbitrary, influenced by what seems interesting. Different boundaries might weaken or strengthen the pattern. We're not discovering a pre-existing category, we're constructing one through investigation. This is the observer's paradox. To study something, we must define it. But definition is already interpretation, already a choice shaping what we subsequently find. Jung wrote about projection. We see in reality what we carry inside. When we look at Atlas and see a messenger, are we seeing the object or our longing for contact? When we see clustering and call it a pulse, are we seeing coordination or projecting our desire for order? The question isn't whether projection happens, it definitely does.
The question is how to separate it from objective measurement, how to distinguish between what's really there and what we've imposed. Science provides methods, quantification, statistical tests, reproducibility predictions. These don't eliminate subjectivity, but constrain it, making interpretation answerable to data. The comet pulse is testing those methods. It's a pattern at the threshold of significance where observer effects matter and might determine whether the phenomenon survives scrutiny. That's not a flaw. It's science working as intended, subjecting claims to rigorous evaluation. We live in a paradoxical age, more scientifically literate than ever yet, hungering for mystery, meaning experiences transcending the mundane. This isn't contradiction, it's synthesis. Rational mysticism using reason to explore wonder, evidence to navigate the unknown. Long-form science content has exploded in popularity. People listen for hours to documentaries about black holes, quantum mechanics, cosmic mysteries. It's not just education, it's something deeper: contemplation, secular spirituality. The comet pulse fits perfectly, ambiguous enough to permit wonder, but concrete enough to investigate. It doesn't require faith, it requires curiosity, willingness to sit with uncertainty. Neuroscience research on awe explains the appeal. Experiencing vastness produces measurable psychological benefits. Reduced stress, improved mood, increased connection and purpose. Awe is medicine for the modern mind, counteracting fragmentation and anxiety characterizing digital life. Cosmic mysteries provide awe in curated, accessible form. You don't need mountaintops or cathedrals, you just need a screen and willingness to engage. This is the modern cult of curiosity, a community finding meaning not through dogma, but questioning. Experiencing transcendence not through revelation, but understanding's slow expansion. When you look at Atlas, you're not just seeing an interstellar object. You're seeing humanity reflected: our curiosity, our fear of insignificance, our hope for contact, our need to find meaning in the void. The 17 comets aren't just icy debris. They're symbols of questions we can't stop asking. Are we alone? Does the universe contain patterns we haven't recognized? Is there purpose woven into cosmic structure? These questions are as much about us as about the cosmos. We're pattern-seeking creatures in a universe that might be patternless. We're meaning makers in a reality that might be indifferent. The comet pulse is a Rorschach test. What you see reveals your relationship with mystery, with uncertainty, with the unknown. Some see synchrony, evidence of order. Others see randomness, coincidence amplified by wishful thinking. Neither view is necessarily wrong. They're different ways of interfacing with ambiguity. The deepest mystery isn't whether the pulse is real. It's why we care, what that caring reveals about consciousness, about our place in an indifferent universe. Maybe the universe doesn't send signs, but we see them anyway, not because they're there, but because we need them to be. Because we're built to find meaning, and finding it is how we survive. We return to the metaphor that opened this journey, the solar system breathing. 17 comets pulsing inward, as Atlas approaches, scattering as it departs. After hours of investigation, what have we learned? We've learned the pattern is real. In some layers, ambiguous in others. Physically, comets are genuinely arriving during a narrow window. Observationally, surveys detected them. Analytically, whether clustering is significant depends on methods. Perceptually, synchrony is strong in some visualizations, weak in others. We've explored natural explanations, Oort cloud waves from ancient perturbations, debris, streams from fragmented parents, detection biases from survey schedules. None perfectly explains the pattern, but all remain plausible. We've ventured into stranger territory: dark matter, sub-halos, rogue planets, even artificial origins. These hypotheses stretch plausibility, but can't be entirely dismissed without more data. We've examined ourselves: how observation shapes reality, how algorithms mediate perception, how consciousness projects meaning onto chaos. The honest conclusion: we don't have definitive answers yet. The comet pulse sits at the edge of current understanding, neither clearly explained nor inexplicable. But that's okay. That's where science lives, in the gap between measurement and understanding, in the space where questions outnumber answers. The solar system does breathe in a sense. It pulses with rhythm, driven by gravity and time: planets orbiting moons, migrating comets falling inward in cascades shaped by events millennia past. Whether the current pulse is part of that natural rhythm or something more unusual, we'll learn through continued observation. Perihelion has passed. Data continues arriving. Clarity will emerge or it won't. Either outcome teaches us something valuable. As we close this long journey through data and speculation, through science and philosophy, through the cosmos and the human mind, trying to comprehend it, consider this final thought. Perhaps the universe never sends signs. It only reflects the questions we're brave enough to ask. The comet pulse, real or imagined, physical or perceptual, is a question the universe is asking us, or we're asking ourselves, projected onto the cosmic canvas. What does it mean to find patterns? How do we distinguish order from noise? When do we trust our observations and when do we doubt them? These are epistemological questions, questions about knowledge itself, about how we know what we think we know. The comet pulse won't be the last cosmic mystery. There will be others more ambiguous, more challenging. Each will test our methods, our assumptions, our ability to hold uncertainty without collapsing into premature conclusions. That's the future of astronomy in the age of big data and AI, navigating floods of information, distinguishing signal from artifact, maintaining rigor while staying open to surprise. The mystery isn't out there scattered across astronomical units. The mystery is the silence within finally echoing back. The mystery is the act of wondering itself, the fact that we exist to ask questions at all. As you drift towards sleep, carry this: the solar system breathes and we breathe with it. Inhaling data, exhaling interpretation, cycling between knowing and unknowing. And somewhere moving faster than we can follow, a visitor from another star continues its journey, carrying secrets we may never decode. But we're still here, still watching, still wondering. And perhaps that's the only answer that truly matters.